Today is June 9th, 2024. We're going to continue about electromagnetism. We'll continue talking about Gauss's law application. Today we're going to be talking about the rod, but this rod is infinite long, and then we try to look at the electric field, which is a distance r away from the rod. Okay, so before we dive into the deeper, let's review what we had last time. So last time, this is the finite length. And then we said there's a charge Q which was uniformly distributed in this finite rod. Okay, and then we ask for the electric field somewhere here. Okay, but this time is different. So those two sides, they can extend it as long as we want to. Okay, so how do we calculate the electric field E right here? We are going to draw a cylinder which serves as the Gaussian plane, right? So in this plane, we can divide them into three sections: the top plate, the cylindrical, and then also the bottom plate. So first, look at the top. The direction of the plane is that direction. Let's say the charge density is named. Why we cannot use the Q in this case? Because this is an infinite amount, right? So typically we use the charge density to represent the charge. And then if we say this is the distance of L, so the whole thing, the whole cylinder is some imaginary cylinder that we have to easier for the calculation. So again, for the top plane, this is the direction of the plane, and the direction of the electric field is going to be that, right, radically. So the angle theta between the top plate and the electric field is this guy right here, is 90 degrees. In other words, if we try to calculate the electric flux, the top one would be the E top dot A top. That would be E top times A top times cosine 90 degrees. So that's the definition of the dot product. So that's equal to 0 because cosine 90 degrees equal to 0. Similarly, the phi E bottom would be E bottom dot A bottom. Again, the direction of E is radically, and the direction of A is that direction. They form 90 degrees. So that will be E bottom times A bottom times cosine 90 degree. Again, that's 0. Now we have to look at the lateral. The lateral, let's say VE middle. So that would be E middle dot A middle. So that would be E middle, the magnitude, dot A middle magnitude times cosine, the angle between those two. Since E is this direction, A is also that direction. So the angle is 0 degree, which equal to 1. So that is gone. So the E middle is exactly the thing we're looking for. So we just use E to represent it. The A middle would be the area of the little cylindrical, right? So the circumference of this circle right here, that's 2 pi r. And then the length is L. So that's the whole surface area. And then E dot A, based on the Gaussian law, that would be Q enclosed divided by epsilon 0, right? So again, let's rewrite this again. E dot 2 pi r L. What is Q enclosed? Q enclosed will be whatever the charge covered in this section. So that was the charge density, lambda, times whatever the length right here, which is L, divided by epsilon 0. Notice L can cancel out. So E is 2 pi r epsilon over lambda. Okay. Again, as the R increase, the whole value is decreased, which is intuitively correct, right? Because if we are far away from this rod right here, then the electric field is going to be weak. Okay, so right now it seems like calculate the electric field is much easier with the application of Gaussian's law. So again, if you are asking to calculate the electric field in in certain geometric location, at least you know two ways. One is the way we introduced at the very beginning. You basically consider about the charge and then how to calculate that. And then another method will be using Gaussian's law. Okay, so that's all I want to share today. Thank you very much. I'll see you guys next time.